Hi there. My name is Richard Ward, and this is the talk with the longest title at the show, or called Windows Vista and Longhorn Server Under the Hood of the Operating System Internals and Your Application. We didn't actually come up with that title. But what we will be covering is what's changing in Windows Vista, what's new in the kernel, what's going on under the hood. We'll be talking about some service controller, the registry, kernel changes, 64-bit things. Basically, just about whatever you're working on will have some impact on what or you'll have some interest in what we're saying. And fundamentally, there are a number of things going on here. We've got changes that we've been working on for many years that we get to show off finally. And these include these areas and other performance improvements, things as a developer that you can take advantage of, new tools, new ways of doing things. Also, things that your customers, the end user, is going to be doing, so you should be aware of what's changing and what you can take advantage of in the system. Kind of boomy. And finally, there's some stuff that we've been working on for a while, and it's just kind of cool. And as developers, you'll be able to appreciate that, and we get a good chance to share these things finally. So, you guys have probably all seen a diagram that looks roughly like this. This is the so-called simplified core diagram, where got the kernel down underneath the kernel user boundary. We've got NTDLL as the major entry point, kernel 32, advapi 32, other user mode DLLs calling down through that layer to get services out of the kernel. And in the kernel is broken up into various functional areas: object manager, security, plug and play, IO manager, all sorts of areas. We're not going to be able to talk about all that today because that's a really big topic. The security guys have done some really cool examples or some really cool work in the reference monitor, but you hopefully have gone to one of the user account protection talks to learn about the integrity levels and things like that that are being added to the system. We're going to focus more on the real core of the kernel before we branch out into user mode, starting down even below the kernel during the boot, moving up through the memory manager and on to user space and so forth. I'll be delivering the first part of the talk. My colleague Karthik Thirumalai will come up afterwards to talk about the service controller changes, service model changes, and then I'll come back on to talk about 64-bit and then dig into all your questions. So what's been going on in the core? First off, we've got a new boot environment. After 12 years or so of dealing with the AT-BIOS world and boot.inis and the initial attempt at the ARC system, the Advanced Risk Computing, for those of you who remember NT4 and 351 in those days, we have a new boot environment that is actually platform and firmware independent finally, which is more appealing to us for an engineering perspective, but it's finally portable. We should be able to take advantage of new hardware as it becomes available and the market and our business people decide it's necessary. And we actually support 32 and 64-bit systems in the single compiled image. And we can handle both BIOS in the old PC-AT model and the new EFI mode that is coming down the road. And finally, since we all know this is a globally connected world, our bootloader is finally localizable. We support a number of languages up front. We support languages that are not in the Latin whatever character set, so we can actually do something useful for people in East Asian countries and other character sets. And it's a big change for us, not so much as a big developer impact, but something we like to show off. For the server side of things, we've got something new for hot add and replace of processors and memory. So long-running servers, not very good if we have to take them down. Reliability numbers go down for servicing and maintenance. Now we will be able to support moving memory off of a particular stick once it's known to be bad. We can move all the actual pages that are in use away from that, let the assuming that the hardware supports it, of course, let the operator remove the stick, replace it with a new one, and then come back on there and make use of that one as well. Likewise, for processors, we can certainly stall a processor, let you replace a busted processor with a new one, or add one in a perhaps in a licensing deal where you could activate a license and get new CPU power, and that's more of an OEM scenario than one of ours, but we're there with the underlying support in the kernel. Finally, back to the consumer space, we're getting a better power management story with a hybrid sleep mode. Instead of either having a simple sleep with everything staying hot, or hibernate where you're waiting on the disk, we have a hybrid sleep model that allows us to combine standby and hibernate, where not everything needs to be spilled to disk right away. We can keep some things in memory on the low power drain. We can suspend, therefore, to RAM and disk at the same time, functionally, leaving the laptop user with a better experience, because they can now shut their lid and not kind of wait for a thing to come out, or hit the power button, wait. They can move on. There will be a talk after this one on power management, which, if you're at all interested in making the laptop user's life better, you should attend. Our memory manager has been taking some changes in lately. One of the most important, again, more on the server functional side than on the laptop or the desktop, is the dynamic system address space support. Here we've got, for those of you who know on the server world, where we can kind of change the user space that's available to applications, the so-called /3GB switch and the subsequent /user VA switch, where we can say, oh, you're going to have 3 gig or 2.5 gig or whatever you need available to your application for it to run best. This is now done without requiring a reboot. We can actually rescale the whole system and support this as a tuning parameter. So no more figuring out how your server's doing, set the switch, reboot, test to see if your application's working better. Now you can just set the value and go with it. Kind of more of a nerdy topic, the VA space kernel page tables are now allocated on demand. Prior to this, we had to pre-allocate a lot of these so that we could handle out-of-memory conditions and still allocate memory in low and reserve space. Now these are allocated dynamically, which frees up more kernel pool for your drivers and for your I/O. So once again, if you're writing a more serious server that's doing a lot of I/O, you can take advantage of more throughput because the pool will be freer. NUMA, or non-uniform memory access, and large page support has gone in as well. NUMA, for those of you in the server world, is a familiar term. For everyone else, that's something where we can go look at, have different chunks of memory associated with different processor clusters, and therefore tune your memory use by process and by actual processor. And finally, back to the consumer space, we have something called, we're paging in video memory. You've all by now seen the glass demos and played with Vista downstairs. You may have noticed that these are fairly intensive uses of DirectX surfaces and, by extension, memory on the video card. The video cards used to have just their fixed amount of memory, and whatever was in there was in there. We are now supporting a way of working with the video drivers themselves to effectively page the memory back off of the video card into main memory, replacing surfaces in this fashion. This is kind of an esoteric point, but it does allow us to create these surfaces on the video card. And then as an application takes up more memory, doing more interesting animations, we can pull the unused surfaces, unused sprites and things like that back off of the card into main memory without having to regenerate all the time. It basically turns into a paging operation, which is much more efficient. Elsewhere in the user space, we have added what we call the user mode driver framework. This is a response to the fact that there are a lot of drivers in the world. We know of some 190,000 unique drivers out there, or something like that. And if one of them goes bad, your system crashes. And this does not lead to a lot of satisfaction in the customer space. So one of the key areas that we're doing in Vista is to create the user mode driver framework, allowing simpler drivers to move out of kernel mode and work in user mode. So even if they have a problem, the failure would be limited to an application and not to take out the entire system. This does not eliminate the possibility of loss of data, but it does make the user a little bit better off than dealing with a blue screen. The infrastructure to run a driver in user mode is actually structured the same as it is in kernel mode. The whole Windows driver framework driver model is designed in such a way that the core objects are presented to the drivers in a way that is agnostic to whether it is user space or kernel space. A well-written driver could even migrate from user space to kernel space and vice versa, depending on the eventual policy of the system. This is not something that we're going to do right away, but it's something that should be appealing to everybody. It's not a new driver model framework that needs to be learned. Once you're in the Windows driver framework model, you've got the understanding necessary for either kernel mode drivers or user space drivers. We have a number of drivers that are coming together for user space already in Vista, and these are mostly in the class of protocol translators. For example, something that's talking to a device on the USB bus really only needs a channel to talk to that thing on the bus, and it doesn't need to have some underlying, doesn't really need to be in kernel mode just to translate. So you'll be seeing more and more of these as time goes by. Another exciting point that we've been working on is our enhanced multimedia support. Multimedia rendering is a popular activity. We like it for our Windows Media Center Edition version, and certainly on laptops. We like to see for, if you've been on a plane, you've probably seen someone watching a DVD or something similar. However, as a general purpose operating system, we're doing a lot of things while someone's trying to render a video stream or an audio stream, and sometimes glitches happen. Frames get dropped, audio spikes, it needs to be resynchronized. This does not lend to a happy consumer experience, since they will be in the middle of the dramatic scene in some particular movie, and then blammo, there's a dropped frame or jaggies or all sorts of pixelation problems. So in Vista, we're introducing the Multimedia Class Scheduler service. The support here is mostly exposed through the Media Foundation that's coming together out of our digital media division. But the support in the base allows for threads to be scheduled at a much finer granularity to demand certain levels of support for how much CPU they need, and therefore work well with other systems. The rendering application can demand up front that it's going to need 70% of the CPU in any given 2-second period, for example, in order to render all the frames and have everything ready to go. We can now make that kind of guarantee come together. We also have support for what we call soft real-time memory allocations. That is, we have inside the Media Foundation has a very optimized and tuned memory allocator that can respond to memory requests during one of these very important time slices and satisfy it without taking certain paging hits, memory extents, all those other problems that cause the control to go away from the media frame or the media application and into the system, and causing a glitch or a drop frame. Finally, as though it sounds very simplified at the bottom, we support something called scheduled file I/O. Now, with the scheduled file I/O support in the kernel, a media framework application can describe that it needs to get a particular I/O operation done in a certain amount of time. Your media framework may decide that needs a 4 megabyte buffer in order to render the whatever video stream appropriately with no glitches for a given second, or whatever the right metric is. By using the scheduled file I/O framework, you can now request that a given I/O or series of I/Os complete in a certain amount of time, and then the system will bend over backwards to make that happen, so that your application, your media framework, can now say, okay, I've got my necessary I/O, and I know that it came in the right amount of time, and I don't have to worry about it. Conversely, on the flip side of scheduled file I/O, we've a low priority application, for example, search engine, virus scanner, disk defragmenter, these sorts of applications can schedule their I/O to take place effectively when nothing else is happening. Drop the priority of the I/O to almost idle time. This allows the search engine, for example, that's in Windows Vista, to come out and say, oh, Mr. IO system, when you get the chance, can you open this file and read it into memory for me? And when it happens, just let me know. I have no time requirements for when it actually happens. That allows the system to prioritize all the real I/O of the user's interactive processes ahead of what the servers, what this, for example, search service would be doing. Now, on the unfortunate side, kernel mode malware has been on the rise. This has been something that we've been seeing come together over time and has kind of driven us towards incorporating more and more security enhancements in the operating system. The other talks, for example, the user account protection and similar talks, you've probably heard about ways that we're reducing privilege for running applications and other ways to, as a system as a whole is enhanced. But the kernel mode malware presents a new category of the problem. Kernel mode malware is code that's running in the kernel space, where it has effectively absolute control over the operating system. It can wend its way into our private data structures. It can hide from user mode applications trying to see what's going on. It can do all sorts of unfortunate things. This code running with the highest privileges can effectively hide in your system and pervert your intents without you ever knowing what's going on. These device drivers can monitor keystrokes. They can see what's going on in your I/O path. They can go install backdoors. They can monitor all your I/O. It's kind of bad stuff. So starting in Windows Vista, we're going to require kernel mode code to be signed. It's not a soft requirement like it was in Windows XP, whereby a driver installation package should be signed, perhaps by WCL or a similar authority. We are going to enforce it both at install and load time. That means that unsigned code will fail to load on Vista. Unfortunately, this is only going to be for x64 in Windows Vista. It's something that we would like to do more completely, but I think market requirements are going to keep it only at x64 for the time being. The mechanism for signing it is being worked out actually as we speak, because there's a meeting going on right now trying to sort all these things out. But by the time Windows Vista ships, x64 drivers will be signed. You will know the publisher of any kernel mode code on your operating system, and therefore you'll know that hopefully the day where a malicious site is dropping a malware rootkit or whatever onto your system, at least on x64, will be set back significantly. User mode code in general will not have this requirement yet. The capability is in the operating system, and we will use it for certain critical system processes. We will be able to configure those to require signed code, and therefore prevent the user mode attacks against various things, or threat injection, etc. So, also in the security enhancement side, we've made a number of changes to the services model, which Karthik will now be able to expound on.
Sure. Thanks, Richard. Only signed code in kernel mode. That's pretty cool, don't you all think? So Richard spoke about the cool code changes we made to the operating system. I'll now do a quick deep dive into the service model and what changed in the service model. So before we do that, let's define what a service is. Depending on who you talk to, a service can mean a different thing. For instance, if you walk down the hall and go to an Indigo talk, service could mean one thing in that talk. Or if you go and talk to the database guys, a service can mean another thing. In this talk, we will restrict our definition of a service to Windows service or NT service, as it's popularly known. So what is a Windows service? They apparently took away one of my slides. So what is a Windows service? A Windows service is a long-running process. It does not require an interactive user to log on and conforms to the service programming model. The service programming model, as most of you are familiar with, consists of three big components. First is the service control manager, or the SCM. This is the heart of the service programming model. This is responsible for registering your service, managing your service, starting and stopping your services. Then we have the services and the service process. Services are usually hosted in service processes, which can host one or more services depending on how they are configured. A good example of a service process would be the service host process, which you see in Windows by default. That can host anywhere between 5 to 40 services, depending on the instance of this process. And then finally, we have the service control programs. These are nothing but your client programs like the Service Control Manager, Snap-in UI, which you go and click on to manage your services, or your command line tools like net.exe and sc.exe. These use the SCM command line APIs to manage services. The service model currently exposes two start types. First is the automatic start, and then we have the manual start. Auto start services are started by the Service Control Manager during boot time. The good thing with auto start services, you don't need a client program to initiate a start command to start the services. Of course, like all good things, there's a flip side to it. The problem is auto start services can have a negative impact on boot performance. Think about 50, 60 services starting up during boot, all trying to access global resources like the registry and competing for the same logs. This will have a significant impact on the boot time. On the other end of the spectrum, we have manual start services, which don't impact boot time, but require a client to start the service. These clients usually start the service whenever a specific scenario is enabled. So one of the first things we did in Vista was to analyze the behavior of auto start services. We looked at a bunch of auto start services and made an interesting observation. Most auto start services are auto start not because they have to provide some functionality during boot. They're auto start simply because they want that unattended start behavior. So we took this observation and introduced a new start type in Vista called delayed start. So delayed start services are started by Service Control Manager a little after the initial boot period in low priority CPU and I/O threads. The delayed start services have best of both worlds. They have the unattended start behavior and do not affect the initial boot performance. And as you can see from the code snippet here, changing your service to a delayed start service is a really, really trivial task. All you need to do is make a single configuration change to your existing services, and boom, you have a delayed start service. Service security model. Services, like any other application or process, run under a specific account. To make management easier, the OS provides 3 built-in accounts. The advantage of these accounts is you don't need a password for these accounts, so you don't have the standard password management issues like expired passwords, changing passwords, etc. Currently, the OS has 3 accounts. First is a local system account, which has pretty much most of the privileges available on the system. This is a very powerful account and should be used with extreme caution. And then we have local service and network service, which is these 2 accounts have a greatly reduced privilege set when compared to the local system account. And this is the recommended account we tell folks to use when they're developing services. So services by default run in session 0, which is a great thing. But unfortunately, before Vista, session 0 was also shared by interactive user applications. This opened up a potential security issue. Consider a service running as local system, and then which has a bug in it. And then you have a malicious user app running in the same session, which could potentially send messages to the service and compromise your whole system. To mitigate this security issue, starting in Vista, user applications are no longer in session 0. They're always started from session 1 and beyond. Of course, this has a downside where existing services that display UI will no longer be visible to the user sessions. But I'm sure all of you will agree that that's a small price to pay for increased security. So the very nature of services, the fact that they're long-running and they have a large install base and usually running with high-privilege accounts, make them attractive targets for malware. Most malwares we have seen out there, like Sasser, Code Red, what have you, take advantage of some issues in a service. To mitigate this, we introduced the new infrastructure called the Windows Service Hardening Framework, which is exposed by the Service Control Manager. Our goal with the Windows Service Hardening Framework was to enable running services with the least privilege, provide service isolation, and then if your service is compromised, make sure your damage potential is constrained. And finally, we wanted to make sure that this can be leveraged by existing services. So we enhanced the existing security model and the programming model in a natural way. So let's look at how we achieve these goals. First is running with least privilege. So most services don't really require all the privileges provided by a given account. For instance, if you take a backup service, it probably needs maybe backup and restore privilege and a couple of other privileges. It probably does not need TCB or take ownership or other dangerous privileges like that. With that in mind, we have a new way to express this in the service control manager service property. So you could express the privileges required by a service as a configuration property. And when your service is started, service control manager will make sure that you get only the privileges you need and strip out all other privileges permanently from the process token. The good thing with this is all you have to do is make a small configuration change using the service control manager APIs or any of the command line tools, and the existing services can leverage this new feature. One thing to remember here is you can not add privileges to a given account. If the account does not have a privilege, you can't add a new privilege to it. For instance, if you have a local service account, you can't express in the property saying, I need TCB privileges. That will not work. And then next was service isolation. Now that we have service running with least privileges, we wanted to provide some kind of isolation for services. Most services, though we provided 3 built-in accounts, network service, local service, and local system, that doesn't really isolate services as most services run with those accounts. So if you have a service that needs to have access resources and wants to make sure nobody else can get to those resources, running in local service probably doesn't help you. To address this issue, we introduced a concept of service SIDS. Service SIDS is really a one-on-one mapping between your service name and a security identifier. So every service gets its own security ID. Service SIDS, as with privilege stripping, is you can opt into this feature by making a small configuration change. And once you do that, when SCM starts your service, it'll add the SID specific to your service to the process token. You can use the same SID using any of the lookup APIs and ACL your resources to allow only that service to access those. So now we have service isolation and running with least privilege, which is great, but we wanted to go one step further and said, if a service is attacked, we want to make sure that the damage potential is constrained. So we took the concept of service SIDS and the existing write-restricted tokens and came up with the concept of restricted services. So for instance, some of you might wonder, why do we need to do this now that we have isolation and reduced privileges? Let me give you an example. You have a service running in local system, for instance. If you have, let's face it, most services, there will be some bug or other in services. And if an attacker comes in and leverages that bug and takes advantage, compromises your service, we want to make sure that your service does not go and access other resources that is open to local system or local service. So with the restricted services, you can only go and write to resources that you have explicit write access to. In other words, the admin or the developer has to say, my service can write only to registry A or file B, and only your service can write only to those. One important thing to note here is if you have multiple services in a process, all services in the process should be restricted. Then we did make some changes to the service management too. One of the common things people want to do with services is they want to know the state of the current given service, and when it changes from a given state, for instance, start to stop, they want to be notified. To do this, historically, people have used polling loops where they keep querying the service state periodically or continuously. The downside to this is it has a huge performance impact, and even worse, people have committed a lot of bugs in those polling loops. To help solve this problem, we introduced new notification APIs, which will actually notify you whenever there's a change in a service state. These APIs work both locally and remotely. So conceivably you could have a single machine in your So you could conceivably have a single machine in your enterprise which will monitor all of your services all over your enterprise, and you could be notified to the central terminal. Then we made some changes to the reliability management front too. As most of you know, Service Control Manager already exposes recovery functionality. When a service process crashes, we have ways to recover that. But we went one step further. We said, crash is not the only case where people want to recover their service. There could be other instances like a service might want to recover in terms of it detects memory leaks and it wants to recycle itself, or it has some other scenario-based errors and it wants to restart. To facilitate this, we added another configuration parameter. That's the key here. Legacy services can take advantage of all these changes. With this called a failure action on non-crash recovery. Using this parameter, once you set this parameter and the service exits with a error code other than error success, you can take specific failure actions. So those were the big changes in the service model. I know that's a lot of stuff to digest in like 10 minutes. So we do have a services lab. I believe it's Fun HOL 19, where you can go try and have a first-hand experience on some of the stuff we spoke about here. So let's switch gears and move on to a completely different subsystem, the Windows registry. Windows registry by far is the most popular configuration store available. It's used by the kernel, drivers, user applications, and anything that wants to store state information. The popularity of the registry comes from its really, really simple programming model. The registry abstracts all the complex data management schemes under and provides a simple hierarchical structured data access. Internally, the registry stores data in registry hives, which is implemented as files. So at a really high level, you could think of the registry as a file system within a file. So under the simple programming model is not really so simple if you look at this diagram. The registry has a bunch of systems interacting between each other to provide a really scalable and reliable data access. So that's the registry before Vista. Let's now look at some of the changes we made in Vista. Actually, all registry operations are atomic, but they are atomic when they are isolated. Every isolated registry operation is atomic. But there has always been a need for providing all or none semantics for a group of registry operations. In Vista, we fixed that by introducing transactional registry. So we added asset semantics to a group of registry operation. Not only that, the transactional registry can collaborate with other transactional resource manager like the transactional file system, so that the transaction can span across registry and the file system. So a good example of a scenario that will use transactions is an installer. If you take typical app install, it probably has a few hundred registry operations and a few hundred file operations. And if your install hits an error in one of those operations, it's the responsibility of the installer to maintain state and clean up all those registry operations you made and the file operations you made. That's a really difficult task and probably impossible in some cases. But now with transactions, once you wrap your install operation in a big global transaction, if you hit an error, all you have to do is roll back the transaction, and you're back to a clean slate again. That's a pretty big change. To learn more about transactions in Vista, there's a session right after this, Fun 320, which will talk about how to use transactional file system and transactional registry. And they ate another slide of mine again. So most of you by now would have heard, actually all of you by now would have heard about user account protection. One of the challenges we faced in enabling user account protection is to be able to run legacy apps as a standard user. As most of you know, legacy apps don't really work well when they are run in an account other than an administrator. To help mitigate this problem, we introduced the concept of registry and file virtualization. Registry virtualization, in a nutshell, is all it really does is it takes a globally impactful write operation and redirects that to a per-user registry location. So this redirection is transparent to the application. So if you have a legacy application running as a standard user, the calls will just work fine, and it'll use the values from a per-user local store. One important thing to remember here is virtualization is just a bridging technology to enable legacy applications. It is not platform support for providing sandboxing. This current implementation of virtualization will probably change the next release, and we might even deprecate it completely once we have all applications moved over to the new model. So enough of what is virtualization. Let's actually look at a quick example of how it works. Let's take the case of a write in a write operation which a legacy app wants to perform. If you have a key, let's say in the software hive, HKLM software, key 1, which has two values, V1 and V2. Let's assume that this key is ACL so that only admins can write to this. If you have a standard user app coming in and writing a new value in here, typically you would have an access denied. But at this point, virtualization kicks in and moves this write to a per-user store in the classes hive. This store is non-roaming, so any local virtualized value will stay specific to your computer. And the call succeeds as far as the application is concerned, and it will just continue working. And read is very similar too. So when a legacy app tries to read key 1, it will read value 1 and value 2 from this system-wide store, and the registry automatically merges the view and gets value 3 from the per-user local store. Another important thing to note in virtualization is when you open a key for write access, the registry will return maximum allowed access for keys that are virtualizable. So not all keys are virtualized. Only keys in the software hive is virtualized. And there are other ways you can turn off virtualization. First is applications that run as that are identified as admin apps, typically installers, are not virtualized. And in the interest of time, I'll skip over this list. A couple of highlights here is callers in curl mode is not virtualized. If the caller is using impersonation, then the operation is not virtualized. Configuring virtualization. Virtualization is globally controlled by the caller's token. So if the caller is, like I said, if the caller is in kernel mode, or if the caller is using impersonation, virtualization is not enabled. You can also control virtualization at the key level by using the new flags option in the reg.exe tool. And finally, you can completely disable virtualization by setting the ACLs on a key such that a standard user can write to the key. A few things every developer should be aware of when using virtualization. First is using the registry for IPC. A classic scenario here is having a service and a front-end client application. A service is usually running in a service account like local service or network service, and your client app is running in an account, the standard user account. A good example of this scenario would be an antivirus service, which is responsible for downloading latest virus signatures, and your client app, which actually initiates the download process. So a user might say, okay, go download the latest antivirus signatures. But the registry virtualization will kick, and if assuming the service and the user app communicates using a registry key, the registry virtualization will kick in as soon as the user says download latest virus signatures, and his notification will be stored in a virtual store. The service will never see that notification, and it'll just continue assuming that there's nothing to do. So this is an important thing to be aware of when you're using the registry to do IPC. Another important thing to remember is impersonated callers are not virtualized. So if you're debugging a weird app behavior and you know that the app uses virtualization, this is probably the first place you want to look at. And lastly, you want to make sure you audit for possible elevation of privilege paths. Remember, virtualization is at the key level, and it's enabled by default only on keys in the software hive. So I mentioned that virtualization is not platform support for sandboxing. That said, we do recognize the need for providing support for sandboxing. There are a bunch of applications in the world, like your antivirus or management apps, which provide solutions for sandboxing. The registry filtering model provides support for monitoring and blocking registry calls. That works for most cases, but there are a few applications that need to be able to modify parameters and redirect calls. And they need the ability to specify specific altitudes. By this, I mean that they want to be able to specify that they can be registered at a particular level on the stack. To fix this, we introduced a new filtering model in Vista. The new filtering model is consistent with the file system filtering model, which most of you are familiar with. This filtering model allows you to specify altitudes for your filter drivers, and in addition, it allows you to redirect calls and modify parameters. And as with every other change, we strive very hard to keep it compatible with legacy technology out there. So the new filtering model will support legacy callbacks, and it will retain the same first-come, first-come semantics for those legacy callbacks. So those are the big changes in Windows registry. I'll hand it back to Richard now to talk about WOW64 support in Vista.
All right. He'll be back in only 15 minutes, so don't worry. So what is WOW64? Our projections show that a lot of the server hardware will be 64-bit capable within a year, at least the new hardware that's being shipped. And certainly on the desktop, we're seeing a lot more 64-bit aware hardware going out. And as soon as the drivers catch up, the signed drivers, of course, catch up, especially with Vista, we should see a lot more customers running 64-bit versions of Windows on their desktops. But as you're probably aware, the vast majority of the software out in the world is 32-bit, which immediately raises the question of what are we going to do with all that 32-bit software on a 64-bit machine? Our answer has been WOW64. It's a 32-bit Windows emulation layer on top of the 64-bit version of Windows. It allows us to maintain a binary compatibility with the existing 32-bit applications and let them run as if it were running on a native x86 processor. But of course, it's running on either AMD 64, an EM64T, or in some scenarios, an IA64 processor. The WOW64 architecture is fairly straightforward, as you can see in this clear diagram. This one warning, the diagram is inverted from your normal view. The kernel is at the top, because this is actually key to the address space as opposed to an architectural pure view. The executive, the kernel at the top, and the Win32K are, of course, native code running at 64 bits. The address space between where kernel mode begins and the high point of 32-bit space is reserved away from the 32-bit process. Even though the 32-bit process appears as a 64-bit process to the system, the addresses that it can't possibly reference because its pointers aren't large enough are out of its range. And if you can see, just buried tiny in there, it's either tops out at 7, FFFFF, or FFFFFF, all the way across. This is actually kind of an interesting point, and I'll come back to it in a few minutes. In the process, there are, in general, only going to be 32-bit versions of DLLs. The exception is the native 64-bit NTDLL, because every process has to have an NTDLL in it in order to talk to the kernel. And then there are three 64-bit support DLLs that allow the process to run in this environment. The classic WOW64 DLL, the WOW64 Win DLL, which is the thing that talks down to the Win32K driver, and then WOW64 CPU DLL, which is the bit of code that actually handles the transitions between the emulated mode and non-emulated mode. Above that, there are only 32-bit processes, or actually, I guess below that in this particular model. But Fundamentally, all the other binaries, all the other DLLs and XZs that can be loaded into this process must be 32-bit. That is all that can be interpreted. So if you attempt to load a 32-bit or load a 64-bit DLL into your 32-bit process, it will fail. So as we noticed, the address space for a 32-bit process is limited to what a 32-bit process can interpret. In general, that could be 2 gigabytes, although if the image itself, the application, is marked as large address aware in the PE header, then we can actually bump this up to 4 gig. So this is one of those nice little cool things that happens on 64-bit Windows. Your 32-bit process now gets 4 gig of address space instead of the 3 gig that you might see on a 32-bit process. That's actually, you get effectively a whole gig extra of virtual address space to play with. Of course, obviously, system DLLs and runtime and everything else will be taking up some of that space, so you're not going to get a pure 4 gig space, but it's pretty close. And if you have an application, a 32-bit server process, or maybe a large rendering application on your client that is maybe doing a codec or something like that, you've got a lot of extra address space now that you can play with, and you get the full allocation space to play with. As I've noted, WoW 64 processes cannot load 64-bit DLLs, except for those 3 or 4 DLLs get wedged in at the beginning during process startup. They just cannot work correctly in there, and therefore they will not load. Not conversely, 64-bit processes can't load 32-bit DLLs either. You can't do the right thing in that space, so we just prevent that from happening altogether. On 64-bit Windows, there is no 16-bit support anymore. Okay, you give him a round of applause for service controller. We're getting rid of 16 bits. That's huge. It's only been 2 decades of letting that waste away. It's time to say goodbye to 16-bit code. It really is. So, is anyone still doing 16-bit code that would admit it in this crowd? No, good. 32-bit kernel drivers, not surprisingly, will not work on a 64-bit system. Kernel space is in the high end of 64 bits, much like it's in the high end of 32 bits on the x86 world. And the driver, if the driver doesn't understand pointers that are longer than 32 bits, it's going to have problems. They need to be ported, and they should support WoW 64 if you have any kind of direct interaction with your driver. Not all drivers accept special ioctls from user mode applications, but those that do need to be aware of where the ioctl is coming from, where the process is, and decide whether the data that comes down needs to be interpreted. I'll come back to that in a few minutes. Your target 64-bit platform may not support all possible features. So your application can call a new API, get native system info, or maybe it's system information, probably info, it's Win32, and that retrieves info about the native system. It's not emulated, it's not hidden, and clearly if you're using it, you're, in theory, a new application and therefore following the new rules. The WoW 64 registry is an interesting little tidbit as well. 2 views of the registry exist on 64-bit Windows, native and WoW 64. That is native, there's a view for native 64-bit applications, and there's a view for 32-bit applications that are being emulated. Native applications see the entire registry as they would normally expect to see it. WoW 64, or the 32-bit applications, see the WoW 64 view of the registry. Why? Well, primarily for compatibility. This separates 32-bit application state from 64-bit application state. Not all. Why is this important? Well, as applications are being ported, we've discovered that, they're writing certain state about what DLLs should be loaded for extensions, or certain values, or binary encoded values that are being blasted into the registry. And the 64-bit version of the application might try and write something that's too large for the 32-bit application to read. And the 32-bit application may write something that's impossible for the 64-bit application to interpret. Allows us to keep both these things in the registry. It provides a safe execution environment for both 32 and 64-bit applications. They are separate, however, and it's very much akin to the virtualization layer that Karthik was talking about earlier. However, it's strictly between 64 and 32-bit processes. Basically, only certain parts of the registry are separated. Most importantly, things under software, where all these things are stored, and the classes. HKey classes root, which is also under software, but it's much larger. So when a WOW64 application or process opens or creates a key, with the WOW64 layer redirects the path of the key if it is found that that path is in one of the keys or one of the areas of the hives that are separated out. Does so by simply inserting the wonderful string WOW6432 node to the path that's being passed down by the application. This allows you to run the 64-bit version of regedit, for example, and you can see in the registry where things have been redirected. If things are going wrong during your application development or porting, you can fix it. There's no magic here. It's just a little sleight of hand to move things off to the side. This is completely transparent for Win32 applications when they're running on the system. It just works. When you're connecting to a system remotely through RegConnect registry, the view that you are going to be returned is based on the caller bitness. On new clients, Windows XP 64 and beyond will pass along the bitness value of the client during the connection, and therefore we can decide if you're going to get the 64-bit view or the 32-bit view. The registry reflection enables us to have 32 and 64-bit applications actually perform interop through COM. This was no small feat. Anyone who does COM can probably appreciate what was going on there. Mirrors the sense of mirroring certain registry keys and values between the 32 and 64-bit sides of the registry or their views. It's an ownership-based reflection. It means that once a key or a class has been defined as 32-bit side, then everything underneath there is also contained and known to the 32-bit side. This actually allows us to do intelligent reflection of the COM server so that a 32-bit COM server can handle a 64-bit client carefully, and vice versa. The rules for the class ID reflection are fairly straightforward. InProc server 32 and InProc handler 32 are not reflected because they're 32. Local server 32 is reflected. That means that they are going to, the reflected version will be available for each side of the bitness. We only delete the reflected keys if they were written by the WOW64 reflecting, the registry reflecting code itself. That way we know that we can clean up after we see something go moving around. So as you're moving around and putting your applications over to 64-bit, you're going to run into some interesting interop issues. Very straightforward to handle, but there are a number of little gotchas that we can walk through. First problem, should be fairly straightforward, is that the pointer type is now 64 bits wide. It's 32 bits, obviously, on the 32-bit systems. On 32-bit systems, x86 didn't care about the alignment of the pointer. That meant that if you decided to reference the pointer on a word boundary or even a byte boundary, it would the processor, the CPU, would absorb it. You wouldn't notice what happened. Doesn't mean that it's free. Under the covers, that processor had to issue 2 reads to memory and put the pieces together, do a barrel shift, all those other operations. So you are getting a performance hit when you use unaligned pointers on 32. You never noticed it because there was never a complaint. On 64-bit, pointers must be aligned. Failure to align the pointer on a 64-bit boundary, on an 8-byte boundary, will result in an exception being thrown. This is surprising to some people the first time they deal with this. Anyone who's been around Windows for a while, when we were running on the RISC platforms like Alpha or MIPS, realized that the pointers were alignment checked on those platforms as well. So if you paid your dues back then, this should be no surprise. Client-server applications that communicate using shared memory on a single machine pose some interesting new problems. When the client is a 32-bit application on the system, on a 64-bit system, and the server is 64-bit or vice versa, each side of that communication channel has a different idea of how the shared memory is going to look based on their pointer size and similar values. You can go very wrong very quickly in this way. Luckily, the failures are pretty straightforward when you discover that your memory is all trashed, but there are two solutions that pop out at you. 32-bit client should write compatible 64-bit structures. Now, the 64-bit server doesn't need to be WoW aware. Both sides just know to use the extra wide form of the structures, and everything works out just fine. That can be expensive. If you're expecting to have only a few of these things, then perhaps you want to compress the memory a little bit. That means you switch this around. The 64-bit server understands the difference between 64-bit clients and 32-bit clients. It now knows the difference between the 32-bit form of memory and the 64-bit form of memory, and it can expand the pointers when it's doing the references or any walking within the memory. This is also a valid solution. It does require the 64-bit server to now understand what its clients are. Perhaps it needs to open them to find out if it's a WoW64 process. The 32-bit client may need to change if the source request is not known to the 64-bit server. That is, if it's issuing a new message and the server doesn't know about it, then it's hard to move forward if the server doesn't know how to interpret a new structure. And finally, you should be very careful about how you expand the pointers. As we pointed out, that the memory space for the 32-bit process actually extends into the 4 gig range, so the high bit is set. That can lead to interesting side effects when you expand that if you do a signed expansion versus unsigned. So the canonical rule, of course, is don't pass a long address to a WoW64 application. There's nothing it can possibly do with it. So how do you convert these things? Here's a quick table. The 32-bit type is a handle. The 64-bit type is going to be a long. And there's little macros for converting long to handle, ulong to pointer, ulong to ulong. There's no need for anything. And long to handle for hwins and so forth. Please use the macros. They will save you time in the long run. No lie, right before we shipped Server SP1, Windows Server 2003 SP1, we found a problem in 2 areas where the code that was written 4 years ago to do pointer expansion had not caught up to the change that allowed the extra 2 gig available to 32-bit processes. It was doing a signed expansion instead of unsigned, and then the pointer that got echoed up to the 64-bit process was out of range for the 32-bit process, and mysterious failures were happening only under load when it was exhausting the lower part of the memory. So it's a real problem if you go wrong. So that's basically all you really need to know about 64-bit. It's just like 32-bit, only wider. How are we doing on time? Actually, we're right on time. We're trying to reserve about 15 minutes for Q&A here. Before we get into that, there's lots of things still going on here at the PDC. Myself, Karthik, we've been hanging out in the Fundamentals Track Lounge, codenamed Fun. I don't know how much fun it is, but it's been very enjoyable to talk to everyone who comes by, and there are a lot of people there that can answer your questions. As I was pointing out, there are 2 labs going on. I don't know where they came up with these abbreviations. The Fundamentals Hands-On Lab 19 and 13. We won't try and come up with any quick talk for that. There are related sessions, transactional NTFS and registry. Is that tomorrow? It's right after this one, and right here, actually, I think, right? It's Fundamentals 320. If you want to understand transactions, this is the place to go. Security and user account protection. They're our close friends. We did a lot of work with them. They already had their sessions, so hopefully you saw them, or you can get the DVD. And finally, a panel that I, my boss, and a couple of my colleagues will be working on tomorrow called Panel 07, Future Directions. We're going to go on about what we're planning for the future. And if you guys want, it's a panel, so we're going to come in with some intro statements, then you're going to ask questions. So come on down. After the PDC, go down to, we've got all sorts of links for what's going on in kernel changes. The user mode driver framework is public. You should definitely download it, give it a good read through. Registry filters. There's a registration point where you can, just like the file system filters, you can register for an altitude, so forth. WoW64, there's a lot of coverage on MSDN on how to write 32-bit applications. for those people who are staying, we're going to have obviously open questions. Fill out your evaluation forms if you like the talk. If you didn't like the talk, our code was fun402, and if you liked it, it's fun417. Apparently there's a prize involved too. I think they're trying to hand out one prize per session, so I don't know what the prize is. It may not be worth filling out the survey, but do it anyway. Anything else we need to cover? No. Okay.
Questions?
Open questions. And there's microphone there, microphone there. It's really booming.
I have a question. You talked about user mode kernel drivers.
User mode what?
User mode kernel drivers.
Yes.
User mode drivers, sorry. And are they think to work for the whole operating system or for single processes? For example, only my application load a driver in user mode, or even a driver that is available to all processes is loaded.
So the question is, when you write a user mode driver, what is the availability of the driver? Is it going to be available to all processes, or whether it's going to be limited to one, whoever loads it first? It depends on the kind of driver you're writing. Some drivers are, if the driver that you wrote opens an underlying driver in an exclusive mode, then only one's going to run. Actually, video drivers are going to be substantially in user mode in Vista. The LDDM, the new driver model that is being used, has a significant chunk of the actual driving and instruction stream for the video cards done in user mode, and that's handled, obviously, everyone's using the video device. So it really depends on what class of driver it is.
But are they loaded in a single process or in different processes?
Like I said, it depends on where it's going. There is a service that starts up that loads a whole bunch of user mode drivers. Some drivers...
Like a service, in
yeah.
other words. It's like a service.
It can be. It really depends. You have to go for the different actual device class that you're interested in writing for and see how it actually maps into the world.
Okay. And can a COM component in 64-bit call a COM component written in 32-bit, or?
Can you say again?
Can a COM component?
Yes.
Can make a call between 64 to 32-bit or not?
Across process. Can a COM component be called or invoked across 32, 64-bit boundaries? The answer is yes, but it must be, of course, across processes. So it has to be an outer proxy.
Not for in-process component?
Pardon?
Not available for in-process?
No, otherwise it would be a 32-bit DLL and a 64-bit process, and that won't work. I'll just track back and forth.
Yeah. What's new with respect to large pages in Vista, and how does it work with a hot add? And the third question is there any notifications for hot add and remove?
Okay, so how do large pages work?
Well, the first question is basically what's new about large pages in Vista? We already had large pages in 2003, so what's new in Vista?
We didn't have user mode support for large pages, did we?
I don't think.
We had kernel mode support for large pages, but I don't think we actually supported the user space.
No, it was already there.
No, okay. Well, that wasn't as new as Landy said. So, okay, your second part was?
Well, the question is how does it work with hot add and remove? Let's say if there is a remove, so if the large page is going to be broken down, and then when let's say you do something like a replace. So if on the memory that you removed was actually a large page, and the memory was removed, it had a...
Okay, so hot out of memory is physical memory, not virtual memory.
Correct.
So your process will never know. Your process may slow down because we're moving all the memory away from it, and a big chunk, a stick of physical memory is bad.
Right, but the unique thing about large pages basically is they're locked. So
Actually, can you walk a little bit closer into the microphone?
The thing about large pages is basically they're locked. So, and I would assume that there is a mapping that is established when large pages are created. But when you actually remove portions of memory that are actually locked, I would assume the kernel has to break down those virtual addresses into smaller pages or something, And when you actually add memory back in, it has to go back and reconstruct all those translations, or maybe it doesn't do it. So
I think it'll move the large page completely over to a different physical stick, depending on the interleave. Yeah.
okay.
So complete allocations are going to change. It's just like a paging operation, right? If they go out of physical memory and they come back in a different physical chunk of memory. It's just that we're controlling it now.
Right, but the thing about it, basically, they're locked, so they're not even paged. So, so when memory is moved, the kernel has to page them out at some point, and then it has to reallocate memory from somewhere else. So, that was the question. So, it's going to break down the large pages to the smaller pages, or is it going to?
No, it should not break down large pages into smaller pages.
Okay.
It should not. Okay. Over the side.
How are you handling the signing of drivers under development?
So the working plan right now is that while we will not enforce the signing requirement while there's a kernel debugger attached. So people who are developing device drivers can just compile, boot, test. It's only when they're released into the wild, if you don't have a kernel debugger attached, that they'll need to be signed.
What about testing?
Sorry, say again?
What if you're testing
If you're testing
your device driver?
in the wild? Or
No, not in the wild, but I mean, do you need a kernel debugger then in order to load?
Well, like I said, as I hinted at, we're working out the signing plan right now. There's a meeting tomorrow, there's a meeting Monday, a whole bunch of other things. The plan is to have very fast turnaround if you have to go out farther, or other exception processing for maybe you could boot into a different mode, things like that, to do your QA before you release it to the wild.
Because that was a problem last time.
We would like to think that we've learned something from the WCL experience, and we're trying to make that better.
Thank you.
Okay.
Question there.
Mike, actually, he kind of asked half of my question, but the other half is the requirement for drivers to be signed. Is that just a server requirement, or will it also be on the Vista client?
It'll be on any x64 client, any Vista x64 and Longhorn server.
Okay. And my other question was regarding the low priority IOs.
Yep.
Who maintains the state of that? I guess, how do you issue a low priority IO? And if I'm writing a mini filter or a file system filter, will I be able to query the state of that IO so that I know that it's a low priority IO?
Yeah.
Do they expose it in Win32 layer?
Well, at the Win32 layer, you'll be. I forget if it's a new function or if it's a new option in the.
It's a flag.
It's a flag.
Okay.
And then eventually it'll wander into the. It'll show up in the ERP, and you'll see it when it comes down.
Got it.
Oh, wait, you're lurking. Okay.
Okay, well, it's actually kind of good because I got a spin-off question on this.
So it's going to be thrashing back and forth, aren't I? Okay.
Regarding the scheduled file I/O, is it just for multimedia, or could we use it we have server applications where we can want to use that type of thing where we can? Is it better than a sync file I/O where we can say, okay, well, we'll do that, but we want it to be scheduled to execute really, really fast?
So I assume everyone heard that. The question is, is scheduled file I/O available for non-media applications? And the easy answer is yes, right? Because the counter or the other example I cited was search engines, antivirus scanners, things like that can schedule their I/O low, and handle it whenever whenever they get a chance, they'll get some. As a server application, yeah, you could schedule your I/O high, or urgent, or with time constraints. You should do so carefully, right? If
we do.
You could thrash yourself out just as badly, and.
Is that possible to assign it for asynchronous operations? It's here are the asynchronous operations, but I want it to be scheduled to really.
I'm not sure if they support async competition.
They definitely support async. I don't know if they have it on sync, but you could just simulate that. Okay. The way that we do synchronous I/O is NT write file goes, oh, well, let me create an event and I'll wait on it. Right? So
right.
You could do the same in user space.
Okay, thanks.
Yeah.
I believe you said some of the critical system processes are going to have to be signed code now. I don't think I heard you right. Did you say that's going to defend against code injection attacks?
So certain processes when Windows Vista will be evaluating what binaries they load to make sure that no one can, or that they're only loading known signed code. So one common thread injection approach is to create a thread at the load library function in the target process and have it load a DLL. That will fail.
Okay.
If you've opened the process up enough to allow it to create a page and then emit code into it and mark the page as execute and then create a thread in it, well, yeah, okay. Don't do that.
Okay,
So we're gonna make sure that, or we're gonna try really hard to make sure that it is much harder to do in Vista and so forth, Windows Vista.
Thank you.
Yeah. Come on, use it.
All right, thanks. Back to the dynamic processor and memory situation.
Okay.
Will there be a registered callback to find out about those changes? I'm thinking about management applications that are making decisions on the basis of those numbers.
That's interesting. What is it? The management API to understand when processors are.
So
or memory
there is
switching.
an API, but that doesn't work quite right. So
Great, let's ship that. All right. So this is not something that the operating system can do by itself. All right. So it'll definitely have to be initiated by some user remote application saying it's time to replace the CPU because someone told me that it's ready, and I don't know what that interface looks like yet. If you want, you can come grab me at the Ask the Experts tonight. We're table 152 for the 30 people left. Come grab me tonight and give me a card or something, and I'll get the info to you if you want.
Thank you.
Okay. Okay, we'll get it.
Me?
Sure.
You mentioned finer grain priority for threading for multimedia apps. Is that API going to be defined, or was that just a private internal agreement?
So right now, in general, the system has been restructured to support finer granularity in the timer. We've cranked the timer interval down. We've got accounting now at the microsecond level for how many ticks anyone got in a particular quantum before they yielded. We're not exposing that whole hog in Windows Vista. We're trying to release it through the Media Foundation to start out with. Once we get a little more practical experience with it, then it would probably come out as a more general system service in the future. Yeah.
You said that it will be possible to control memory leaks in services in Vista. Did you mean the memory leaks or handle leaks too?
So the service controller manager by itself does not do anything. So we just provide a support for you to restart your service on non-crash. So one example I gave was memory leaks. So if your service is aware of memory leaks, it knows through some monitoring app or through some management app which informs your service, hey, you need to restart yourself because you're leaking too much memory. Then you can use this new support to restart yourself.
So service must determine himself there's some memory leak or handle leak, right?
Yes, service by himself or using another third-party application.
Okay,
Yep.
Mm-hmm.
Does that mean you're going to export that out to the Windows Error Reporting Service so that those types of activities will be visible?
I'm sorry, can you repeat the question again, please?
So if you're going to do like, I'm crashing myself, error restart, are you going to make that visible to the Windows Error Reporting Service? So you would get many dumps and have some chance of...
So if you crash, Windows Error Reporting Service will catch that.
You already have that.
Yep.
Right.
But if you do it fail fast.
Non-crashing crashes.
Non-crash failures, you don't by default get Windows Error Reporting dumps.
Right, but you might think about providing some form of that because that would be valuable information to come back.
Sure, we could probably add some hooks there for you to call those things when you're failing and send those dumps back to you.
Okay, we just got the universal sign of, so we got 2 more questions and then come to the Ask the Expert session.
Just a quick question about scheduled I/O. Can you determine like a timeout, a certain timeout that the operation must complete in a minute, or it's not possible?
Modulo, all the other, failures, like if the disk gets yanked, there's nothing we can do about it, kind of stuff. But you should, part of the urgency side, the multimedia side, is say I need this much of the file read in this amount of time so that I can not glitch. So yes.
Okay, thanks.
And one more question back there.
Yeah, registry reflection.
Oh boy.
You realize how many things that's going to break.
Seems to be working pretty well, actually.
Okay, so here's the question. Registry reflection, does that go into effect if there's an ACL deny? Is that the only time it goes into effect is if a user attempts to
are you thinking,
write
wait. Are you thinking reflection or virtualization?
Virtualization.
Okay.
That's probably going to be a longer answer than we have time for. So why don't you
can
come
grab us offline and we can chat about that.
Okay. And it's the handoff.